Um, Previous class, we worked on a interpolating high order single polynomial through a set of discrete data points. Today's class, we're going to focus mostly on a piecewise set of lower order polynomials to pass through a set of data points. So both of those procedures with one high order polynomial through a set of data points or a set of low order quadratics, cubics through a set of data points are ways of mathematically drawing a line through a set of data points and mathematically learning from that set of data points. And so we're going to compare those two cases. A advantage in past of the high order single polynomial through a set of data points was that it was mathematically less complicated, less time consuming before the age of computers. Whereas what we will call a spline, piecewise collection of low order polynomials was mathematically more complicated procedure and taxing procedure before computers. Nowadays, that discrimination between more laborsome, less laborsome, of a high order polynomial or piecewise low order polynomials doesn't really apply in the age of computers and computing. So we'll explore that. There is one advantage to a piecewise low order interpolation over the high order polynomial interpretation, in that the high order polynomial interpolation suffers a problem at the edges of the region of interpolation. So at the bookends of the region of interpolation, it will oscillate. It contains high order terms in the polynomial. These high order terms in the polynomial vary rapidly. That causes oscillations at the end of the range of the polynomial. The piecewise low order spline of polynomials that does not have the high order terms in the polynomials. It does not suffer the rapid oscillations due to the high order terms. And so that is better behaved at the extremes of the polynomial, at the extremes of the range. I'll also, as well as talking a bit about the high order polynomial and the piecewise spline low order polynomials, I'll mention one other way that, as by way of an introduction to machine learning, we can interpolate with a neural network. And I'll just show you the same problem that will interpolate with a high order polynomial and with a piecewise spline interpolated with a neural network. Okay, this was the type of problem we're trying to solve. You're often faced with in data, you're often faced with discrete data, and you want to interpolate between the points, data points. These are just two examples of a profile of beam in an experiment I'm familiar with, G-2, profile of the magnetic field in the region of beam in this G-2 experiment that I'm familiar with. And those are discrete sets of data, the measurements of the magnetic field and the measurements of the beam, and you want to interpolate the measurements of the beam and the measurements of the magnetic field smoothly. So we want to learn from the discrete data and get a smooth function that passes through the data. And so this is sort of a classic case of interpolation. This is interpolation in 2 dimensions here. The beam is measured in X and Y. The magnetic field is measured in X and Y. So there's 2 independent variables. In our coding examples, we're going to focus on one-dimensional data where there's one independent variable and one dependent variable. This is just to introduce piecewise splines, and compare it with these higher order polynomial interpolations. So a piecewise spline is another way of matching the data points, just like the higher order polynomial was matching the data points. So for example, if you have 10 data points, and I've got 10 data points in this example here, they're in magenta. I can put a high order polynomial going up to ninth order through that set of data points. And that's what the blue curve is the high order polynomial passing through those data points. And you see here the difficulty with the high order polynomial through the set of data points is because there are terms of such high order at the bookends, at the extremes on the left and right, you get oscillations in the interpolating function. So way over here on the left, there's this oscillation near the left-hand bookend. Way over here on the right, oscillation near the right-hand bookend, because we're interpolating a high-order polynomial. So a piecewise spline is a different procedure in which instead of using one polynomial for the whole set of data, you use a reduced you fit little regions, little discrete regions of your range of data to lower order polynomials, and you match them at the boundaries between these different regions where you're putting the lower order polynomials. So let me go to the next slide to show you that. I'll make some comments on that. So these piecewise splines actually initiated before computers. Piecewise splines were done mechanically to form smooth curves if you use strips of wood or strips of plastic. And so this was actually the piecewise splines idea is credited to General Motors. But the basic idea is we're going to put a low order polynomial between pairs of data points in this graph. And so you could imagine what would be the simplest thing. We would put a straight line between each pair of data points on this curve. That would be a linear piecewise spline. We can do a little better if we put a quadratic between each of the pair of data points. Now, with the linear interpolating function between the pairs of data points, the left-hand and the right-hand points determine the straight line, the linear function between the data points. If you have a quadratic between the two data points, between a left-hand and right-hand data point, you need an additional constraint. And that constraint is typically the fact that you're going to say that the slope of the spline on the left of the data point and the spline on the right of the data point would be continuous. So you would get an extra constraint from that. And so in that way, you could do a quadratic between pairs of data points, and that would make a smoother interpolation between the data points. And you're using an additional constraint of the fact that the slope is continuous, as well as the spline passing through all the data points. And then what we're going to talk about today is cubic spline. So this is extending that idea. Between each pair of data points, again, there will be a cubic function. The cubic function we're going to enforce to go through the pairs of data points, just like we enforce the linear function to pass through the two data points at its ends, and for the quadratic function to pass through the two data points at its ends. We're going to further constrain the cubic that the slope of the cubic on the left of the data point and the right of the data point matches smoothly. And then we're going to grab one more constraint, in that not only is the slope at a given data point for the cubic on the left and the cubic on the right smooth, but we'll make the curvature, the slope of the slope, smooth. And so this line in green here is, I've got 10 data points. I've got 9 little regions between pairs of data points. Each of the 9 little regions has a interpolating cubic. That interpolating cubic goes through the points at either end of that region between data points, and it joins the neighboring data points smoothly in the sense that the slope is continuous and also that the curvature is continuous. So this is another way of interpolating data that doesn't suffer from the high order polynomial problem of the bookend oscillations. Okay. So let's see if we can do what we did in the last class, where we set up equations to determine the coefficients of the high order polynomial. We're going to set up a series of equations to determine the coefficients of the piecewise spline. So the many cubic functions that are going to interpolate the data. And so on this slide, I'm just asking us to imagine we've got a set of data points. So here's a bunch of data points from the first data point, x1, y1, to the last data point, xn, yn. So a total of n data points. And we're going to, between each pair of data points, put a cubic function that passes through the data points and joins with the adjacent cubic functions smoothly in the sense that the slope and the curvature is continuous. So just to give an example here, if I've got n data points, which I've got on this plot here, the regions between 2 data points add up to n-1 regions. So I'm going to have n-1 total splines, or total 1 cubics, and we're going to apply the constraints of going through the data points, of having a smooth slope, having a smooth curvature on those cubics. Here's an example. This is going to be my sort of notation for the cubics. Here's an example of a cubic. It's got 4 coefficients. And I'm going to call them A, B, C, and D, and I'm going to label them with an index to indicate what pair of points they're between. And we're going to have n-1 of these cubics with their 4 parameters. And so I'm going to have a total of 4 times n-1 parameters to determine. In order to interpolate the data. So I've got 4 times n-1 parameters to determine. I'm going to need 4 constraints, 4 times n-1 constraints. So where are these constraints going to come from? The first constraint that we had mentioned is that a given cubic is going to pass through the point on the left of the region in which the cubic lives and the point on the right of the region in which the cubic lives. So that for each cubic, there are 2 constraints based on intercepting the points at the ends of its region. And so that's what I've listed here, upstairs here, for cubic SI. So this is the ith cubic between a pair of points. At the left-hand sort of bookend of the region of interest for that cubic, it must pass through the data point. So that's this statement here. And at the right-hand side of the region for that cubic, it must pass through the data point xi plus 1 and yi plus 1. So that's a pair of constraints for every cubic. So actually that supplies half the constraints that we need. We need 4 constraints for every cubic, because there's 4 coefficients in the cubic expression. And 2 of the constraints are always going to be coming from the demand that the cubic passes through the points on the left and right of its region. Need 2 more constraints. The next constraints come from the fact that we're going to require that the slope, when we cross from one region of one cubic to the neighboring region of the next cubic, is continuous. That means that the first order differential of the cubic on kind of the left-hand side of a data point and on the right-hand side of the data point, that must be continuous. So one more constraint comes from setting the slopes, or the first order differentials of the cubics on either side of a data point to be equal to one another. And for that's going to produce a number of constraints. And then we do the same thing with the curvature. We're going to enforce the fact that the curvature, think of a data point, think of the cubic on the left of it, think of a cubic on the right of it. That curvature is going to be continuous as we walk across that data point. That means that the second order differential of the cubics on either side, the left or right of a data point, must be equal to one another. And so those 2 constraints on the slope being continuous at a data point and the curvature being continuous at a data point are these 2 constraints that I've written down here. So the primes indicate the first order differentials, the double primes, the second order differentials. And we're saying that at this point, xi plus 1, which is the boundary between one cubic, the SI cubic, and the neighboring cubic, SI plus 1 cubic, those slopes have to be equal to one another, and those curvatures have to be equal to one another. So that provides almost all the remaining constraints. The only 2 additional constraints that we need are because at the far left and the far right, if you look on the plot, those points that are the bookends, sort of the point with the lowest value of x and the point with the highest value of x, those constraints on the curvature and the slope can't be applied there, because they don't have a cubic function outside this region of interest to the data points. So what we do there is we apply a naturalness to get the remaining constraints. We basically apply a naturalness condition. And what we're going to apply as a naturalness condition is that the second order differential of the cubic on the far left and the cubic on the far right, so the bookend cubics, at the endpoints on the far left and far right, we're going to assume that those second order differentials are 0. That's called an unbiased constraint on the cubics at the far left and far right. It just says, well, we don't know what happens to those cubics outside the region of interest. Let's just assume that there's no bias for their curvature to change in a positive direction or a negative direction. Whatever their slope is at the endpoint, it's not changing at that point. And so that's a constraint, there's an unbiased constraint, and you could imagine inventing other types of constraints there, but we're going to work with what is commonly worked with, which is this unbiased constraint. Anyway, if you add up all these constraints intercepting the points for the interior splines, having them dovetail together with smooth slopes and smooth curvatures, and for the endpoint splines have this naturalness condition that provides the 4 times n minus 1 constraints that we need. So these are the constraints that we'll use. Okay, So just to give you an more concrete example, on this slide and on the next few slides, I tried to enumerate all of this for an example where you've got three data points. So if you've got three data points, and on my plot here, I've got three data points. I've got x1, y1, x2, y2, x3, y3. These are my three data points, and I want to put my piecewise cubic spline through these three data points. So firstly, if I've got three data points and I want to use a piecewise cubic spline, there's going to be two cubics. There's going to be a cubic between the first data point, x1, y1, and the second data point, x2, y2. And then there's going to be a second cubic between the point x2, y2 and x3, y3. So we've got two cubic functions. If I've got two cubic functions, then how many coefficients of the cubics have I got? Was for a cubic, we got four coefficients. I got two of the cubics, so I've got 8 coefficients to determine. So that's the first thing, that I need 8 coefficients to be determined by the facts that I'm going to pass through the data points. I'm going to have continuous slopes and continuous curvatures at the boundary data point. This x2, y2 is the boundary between the two cubics. And at the bookends, I'm going to apply this naturalness condition. So that's where I'm going to get all these constraints from. And so here I'm just rather laboriously enumerating these constraints on the coefficients of the first cubic, so they're A1, B1, C1, D1, and the coefficients of the second cubic, they're A2, B2, C2, and D2. So upstairs here, I've got, for the first two lines are the cubic S1, the spline S1 intercepts the points x1, y1, and x2, y2. That's these upstairs equations here, the top two. The second pair of equations are that the second cubic intercepts the 2 points at either ends of that cubic's range. So intercepts x2, y2, and x3, y3. So those are the intersections. And that's 4 constraints in total. We need 8. There's one point at which these two cubics meet one another. That's x2, y2. We call that point a knot, or a joint between the two cubics. We're going to enforce that knot, or the joint between the two cubics, that they join smoothly, that their first order, second order derivatives are equal at that point. And so that's these second two equations here. So if you look at the first of those, you can spot here the derivative of the first cubic, the derivative of the second cubic, and I'm just enforcing those two derivatives to be equal to one another, the difference to be 0. And if you look at the second equation, you can spot that these two second equations are the second order differential of the first cubic here on the left, second order differential, the second cubic here on the right, and I'm just enforcing that they're equal, that their difference is 0. And so these are the smoothness constraints. So that gives me 2 more constraints. So we've now got 6 of the 8 that we need. We said that these smoothness constraints work for the points that are between the bookends of the data. Here we've only got 1 point between the bookend of the data because we've only got 3 data points. The bookends themselves are dealt with differently to get constraints. And this is how we're, with the naturalness condition, getting 2 more constraints. We're going to enforce that the second order differential of the spline on the left is 0 at the leftmost point. That's this equation here. And we're going to enforce that the second order differential of the spline on the right-hand side is 0 at the rightmost point. And that's this constraint here. And so that totals up on the left-hand side to 8 constraints. We needed 8 constraints for our 2 splines of cubics, with each carrying four coefficients. And so this is how we can arrange to determine, with 8 constraints, we can determine our 8 coefficients, like we might determine two coefficients with 2 simultaneous equations. We got 8 simultaneous equations and 8 parameters to determine. So at this point, we've turned this problem into a linear algebra problem, kind of like the linear algebra problem from the single interpolating polynomial. It's just that the equations of the linear algebra problem are determined in a different way. So upstairs on the left-hand side is enumerating in matrix form the 8 equations that constrain the 8 coefficients in our cubic spline to our 3 data points. So if you look at this matrix algebra equation upstairs here, you see the dependent variable over here on the right-hand side in this vector. You see the independent variable, the x is over here on the left-hand side in this matrix. And you see the coefficients of the splines, the cubic splines, the 2 cubic splines in this column vector here. And upstairs here, I've just written it in terms of, more generally, in terms of the x1, x2, x3 values of the independent variable, and y1, y2, y3 values of the dependent variable. And then downstairs here, I filled in the values that we know, right? We know the data points, so we know the dependent and independent variables. We can fill those in. We see that what we're trying to solve for with matrix algebra is these coefficients of this vector that multiplies this matrix and yields this vector here that contains the independent variable. So this is basically matrix algebra problem. I'm not going to go through all the next slides, but let me just show you that they are equivalent to the equations that we wrote down for the constraints on the cubic spline. So imagine multiplying the matrix by this column vector here to get the right-hand side. Let's just imagine we're going to multiply the top row of the matrix by that column vector. If you multiply the top value of the matrix, which basically has in the first terms x cubed, x1 cubed, x1 squared, x1, and then unity, by that column vector with the coefficients, that is simply the left-hand cubic spline. And the fact that that will equal y1 is that first constraint, that the cubic spline goes through the left-hand data point. The next 2 rows are that the left-hand cubic spline and the right-hand cubic spline go through the data point x2, y2. So go through this point here. So that's rows 2 and 3. And then the 4th row is that 4th intercepting constraint, that the right-hand cubic spline goes through this right-hand data point. In the bottom 4 rows, are the other constraints. So the bottom 4 rows correspond to the constraints on the slope. So these 3s and 2s, these numbers in this matrix here, are emerging from the differentials of the powers of x cubed or the powers of x squared. And then the row below that, the sixth row, is coming from the constraint that the curvature is continuous. And the numbers in here, the sixes and the twos, are coming from the second order differentials of the cubic spline to compute the curvature. So those where those come from. And then finally, the bottom two rows are the constraints on the bookends, this naturalness condition on the bookends. Anyway, we've set up these matrices. They have this form and of the matrix M multiplied by the vector containing the cubic coefficients that we want to solve for equals this second vector here that's on the right-hand side that just contains the known values of the dependent observable, dependent variable. We can rearrange this equation, or we can multiply through by the inverse of M to get a expression for the vector A, and to solve for the vector A as the product of the inverse of M times the vector V. So we put all the known quantities on the right-hand side. So inside M is the independent variable, inside B is the dependent variable, and we can solve for these coefficients of the piecewise polynomials. And we can do that with linear algebra. So I think at that point, I'm just gonna go to the code. So this is my code for solving the interpolation using cubic splines for 3 data points. So it's just going to use 2 splines that deploys these conditions that we intercept the data points, that we have a smooth transition between the 2 splines, that the slope and the curvature are continuous, and a naturalness condition on the far left, far right regions of the splines, that their curvature is 0 at the bookend. So it's going to apply those constraints. And we're going to, firstly, we're going to use our matrix algebra method to solve the problem. And then we'll use, of course, there's a Python package that will solve the problem. We'll solve the problem that way. And then finally, I'll just show you that another way of solving the problem is with neural networks. And I'll just sort of give you an illustration of how we might use neural networks to solve the problem. Okay, so I need a set of 3 data points. That's the first cell here. I'm defining a set of 3 data points. I've defined them in a little bit of a funny way, a little bit of a strange way. It's because of how I later build the matrix M that contains the independent variable, and how I build the vector B that contains the dependent variable. So I defined the individual data points through these scalar variables here, x0, x1, x2, y0, 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 y1, y2, just because that was convenient for me later on. I then pack them together in a Python list so that X is a list of the 3 data point independent variables, and Y is the corresponding list of the dependent variables. And here I just printed them out. In this cell, I also made, when we come to plotting the spline that goes through the 3 data points, I want to plot it as a continuous function through the 3 data points. I need a proxy for a continuous independent variable. So I define this independent variable XS, X spline, that is finely spaced points from the left-hand region of the data points to the right-hand region of the data points in the independent variable. So this is just going to be my kind of proxy for my independent variable. We've done this a lot. Okay. So the first way I tried to solve the problem through matrix algebra was the problem that you've got in solving through matrix algebra is not the matrix algebra step of solving given a matrix and a vector to find the vector coefficients, because we can just call our linear algebra function solve to solve the linear algebra problem. So that's not a problem. That's one simple line of code. The problem is setting up the problem for a given matrix and a given vector to solve for the vector of coefficients. The problem is setting up that given matrix M and setting up that vector B. And so in this cell, I'm just setting up the matrix M and the matrix B that we had discussed in the slides. So if you remember the matrix B, it just contains the values of the dependent variable for the 3 data points. The one here is from the first data point, so this is y1. The 3 here is from the second data point, but it appears twice here because it provides 2 constraints, one on the left hand and one on the right hand spline, and then this third data point, this is y3, which is just a constraint on the right hand spline. Anyway, that's simple to build. The thing that was painful to build was this 64 element matrix, which contains the values of the independent variable, so x1, y1, y2. It contains them as they enter in the 2 cubic splines, so evaluated at the points corresponding to the 2 cubic splines, but it also evaluates them with the first and second order differentials of the cubic splines. So it's a little bit of calculation to fill in all these numbers. So I found it, firstly, I put a comment here. This is after putting in all these numbers, this is how I felt about it. Firstly, this was extremely laborious, putting in these 64 numbers and getting them right. Secondly, it's completely opaque as to what I'm doing. It's completely opaque that this is derived from 4 intercepts. That's understandable. A slope being continuous and a curvature being continuous and the naturalness constraint. So that's completely opaque in this way of forming the matrix. It was if you do this, it's very error prone, right? You make one mistake in typing in the numbers and you got an error. Also, if I change the 3 data points, you've got to change the whole matrix again. So in all those ways, opaqueness, laborious, error prone, non-generalizable, this is a bad way of doing this. So after doing that, which I did in the end, I think get right. I tried this way. So this way is a little bit less opaque. So it's more transparent and it's more generalizable. So it's less specific. So when I construct the matrix, I did it row by row here. But when I constructed the the matrix, I'm putting in, firstly, I'm putting in the x0, the dependent variable, independent variable. So the x0, the x1, the x2 as the variables rather than the numerical values. So that at least makes it generalizable to changing the data points x0, x1, x2, changing the dependent variables y1, y0, y1, y2. So it's more generalizable. Also, I felt that it made it more transparent in that you can literally see here the cubic that's on the left-hand side. And you can see down here the cubic that's on the right-hand side. So you can see where the cubics are. You can see the method, basically. You can see what else can we see in here? We can see, for example, that these two lines are a constraint on both the left-hand and right-hand splines from the same data point, from that data point in the middle. You can also kind of see that based on the values of the coefficients now, these are the values of these values of coefficients are from the first order differentials of the cubic spline. So you can spot the first order differential. And likewise down here, you can spot the second order differential as the basis for this constraint. So it's a little bit less opaque, and it's certainly more generalizable. I think, and it's less prone to making a numerical mistake. So those are the virtues of that. But anyway, I got them to agree in the end. So I was pleased about that. I did think afterwards, maybe there's an even better. We talked in the last class about these polynomial objects in NumPy. So you can make an object that is a polynomial. These polynomial objects have, so you could make an object that is spline 1 on the left-hand side, an object that's spline 2 on the right-hand side. Those polynomial objects have methods that you can use with them. We looked at some methods for printing them, for getting the coefficients, but there's methods for the derivatives of them. So there's probably a even more transparent, maybe more compact, more explicit and clear way of building that matrix by using so if you want to think about it, by using polynomial objects and using the differential method that would allow you, that you could apply to a polynomial. But by then I've kind of packed it in. Okay. Well, once we got the matrix M and we got the vector B, we can just solve the matrix equation that MA equals B for A. And A, remember, contains the coefficients of the polynomials. So the first 4 coefficients in A are the 4 coefficients of the left-hand cubic, spline 1, and the second 4 coefficients in the vector A are the 4 coefficients of the right-hand spline, spline 2. So solving the problem just comes down to this core. We've used this in the last class. We've used it in fitting. Its 2 arguments are the matrix, inverse matrix M. Remember that matrix M contains the independent variable, and the vector B that contains the dependent variable. So this is where the data points are on the right-hand side, and it's going to return the vector A containing the coefficients. Spline number 1 on the left-hand side, so the one that's joining the first and the second data points, I can then construct using remember my proxy for a continuous variable that I defined, xs. I can construct a proxy for the continuous left-hand spline S1 in this way here by just multiplying the terms in powers of x by the appropriate coefficients. So just by hand stripping out the coefficients, the first 4 coefficients, and then do the same thing for the second spline. So this is the right-hand spline that goes through the center point, and the right-hand point, again, it's just stripping out the individual coefficients of the powers of x from that vector A, and doing that by hand. I also made I joined together, so I dovetailed together these two cubics, the one on the left and the one on the right, to make the complete spline through my 3-point data set. So this function call here in num_p, concatenate, it joins together it will join together 2 arrays or 2 vectors. We're thinking of it in this case. So I'm using it to join together the array which is a proxy for S1, the continuous variable X1, and the array S2 that's a proxy for the continuous variable S2. So these 2 cubics. When I join them together, though, I do have to be careful. So because I built them out of this independent variable proxy XS, S1 spans the whole range of the data. S2 spans the whole range of the data. S1, though, is only valid between the first pair of data points, and S2 only valid between the second pair of data points. So when I join them together to make the spline that goes through the whole data points, using slicing, I only use the bottom half of S1, and I splice that together, or dovetail it together with the top half of S2. So I'm putting together S1 in the region between the first data points pair with S2 in the region between the second data point pair to make YS. And then I'm going to plot that. And so here's the result. Magenta, I've got the 3 data points. In red is the first cubic spline, is the left-hand cubic spline that goes through the first 2 data points, the left hand and the center one. And then over in this region on the right, it's where it's invalid. So we see it in the region where it's invalid because it's not developed or designed to match the data on the right-hand side. It's just designed to pass through the 2 left-hand data points and join at the center data point with smoothness, with smooth continuous slope and continuous curvature. So you can see this hatched line. This is where S1 is, and then it diverges over here on the right. S2 is the blue line. You see it clearly where it's invalid, right, between the first pair of data points. It's valid in this region between the second pair of data points. And so here you see it interpolating between X2 and X1, or Y2 and Y1. And then also you'll see that it's designed to join smoothly in terms of continuous slope and continuous curvature with spline S1 at this data point here. The yellow line that you see that passes through all 3 data points is this concatenation that I made of these 2 cubics. And so that is our cubic spline through 3 data points. We've solved the problem with some labor with linear algebra. The easy bit was the linear algebra calling NumPy functions, the harder bit was constructing the vectors and the matrix especially. But that's how a cubic spline works. Yep.
So am I correct in thinking that normally if you're using a cubic polynomial, it's probably traditionally because you have 4 data points, right? Is there a specific reason that cubic is used to link just two data points in this one?
Yeah, so our cubics have 4 coefficients.
4 coefficients.
They both, the one on the left and the one on the right had 4 coefficients because we needed to find in total 8 coefficients.
Right.
So that is what a cubic looks like. I'm not trying to put a single cubic through these 3 data points. I'm not trying to do that.
Right.
I'm trying to develop a method that puts a smooth curve through a set of data points.
Yeah.
And my smooth curve, I said I would make by combining cubics between each pair of data points in a smooth way.
Yeah.
So
why is it a cubic for a pair of data points? Like, because you said that you don't specifically gain.
Yeah.
You don't specifically gain
It's a really good question. So why wouldn't I do what would be the simplest thing? What would be a linear function?
Well, linear spline would just be piecewise.
You get a kink there.
Yeah.
So let's do a quadratic. That would be the next simplest. Quadratic, well, you would have a kink in the slope here.
That's what I was, okay.
So you would have a kink in the slope. So cubic is often what's used because it really does appear smooth in that both the slope and the curvature are smooth. Of course, even with the cubic spline, if I was to look at, I don't know what comes after slope and curvature, and there's another jerk. Yeah, there's a jerk in forces, isn't it?
Yeah.
So that there would be a kink in the jerk.
Okay, that makes
in this case. So, I mean, if that was important to you, you'd want to use a 4th power.
Okay.
But the challenge.
Okay.
So we went linear, quadratic, cubic, saying, well, the penalty we're paying is more and more coefficients,
Right.
needing more and more constraints, and more complexity.
Right.
But cubic is often used because it becomes smooth by eye.
Yeah.
We
don't care about the jerk.
Yeah. We don't care about it in general.
Okay. That makes sense. Thank you.
Yeah, so that was a very good question. Why? Because the question was, why were we doing this?
Yeah.
This is why we're doing this. This cell, I mean, of course, I want to show you that we went to a lot of work in making the matrix and the linear algebra, but there is a function that we can call. Let me show you where in psi p. So we got a lot of functions from psi p. We got all those filtering functions from psi p. We got I think the Lagrange basis polynomials from psi p. There's an interpolate function in psi p, and we can just call that to get a professional level solution to the problem. So here I'm solving it by calling psi p with my data set. So the first 2 arguments are the independent variable and the dependent variable for my data points. And then there's a 3rd argument that I'm using here was, that there wasn't kind of an assumption that we built in to get enough constraints. It was what we call this naturalness consumption to get sufficient constraints. We said we're going to have 0 curvature of our spline on the far left and the far right. So it's sort of an assumption rather than a defining constraint. And so if you want to use that assumption, you would call provide this argument for this for the cubic spline. And there are, if you look up I can't remember them, but if you look up the manual for cubic spline, there's other assumptions that you can use for the endpoints. Anyway, calling cubic spline with the data and your boundary condition, it returns a object which is the spline. So this is like a polynomial object, and it has methods like a polynomial object, but it's not a single polynomial. It's this piecewise polynomial through your data points. Just to advertise some of the methods that come with it, we can print the coefficients of the spline. So I'll show you in a moment, but we can print out what the coefficients of the spline are. You can print the knots or the breakpoints or the joints in the spline. So you can see where the joints are in the spine with this method here. You can take the derivatives and the integrals of the spline, like you could take derivatives or integrals of the polynomials. So it's an object that comes with a family of methods that are rather similar to the polynomial object in the methods that it has. Anyway, once I got the spline object, kind of like we did for a polynomial object, if I want a proxy for a variable representing the spline, I can call the spline object with an array of my independent variable, so the xs, and it will return an array ys of my dependent variable representing the spline. And so I can plot that. Yeah, so I ran that. These are the coefficients of the two splines. We printed out, asked it to print out the coefficients. So left-hand side is one of the splines, the left-hand spline, and the right-hand side is the other spline. The breakpoints, so the breakpoints are the center point, that's a knot, and then the bookends at the left and right. So we'll plot all the, or list all the breakpoints. Here's the result. In this case, the dashed yellow line is the spline from that function core, and I'm just overlaying the results S1 and S2 I got from our hand calculation, just to verify that our hand calculation kind of lines up with the function call from cubic spline. But all that seems to work. Okay. The homework assignment, our last homework assignment, was it 29 homework assignments? Because 29 classes, this just to apply the cubic spline and the high order polynomial to another set of data. Yeah.
Was it intentional to make the assignment 29 due to at 2 p.m. in roughly half an hour?
No, it wasn't. Did I do that?
It seems like you did.
Yeah, so I better change that, and it will be next Tuesday. I'll make it Tuesday next day. I mean, actually, doesn't really. Yeah, I'll make it next Tuesday. That's fine. It's sort of irrelevant with respect to a class, though, isn't it? I could make it due the end of next week. I mean, yeah. I mean, you might want to just get it out the way, right? Yeah, but you don't want it to be at the end of the
December at 2 p.m.
Yes, that's a mistake. Let's see if I can change that. Where are we?
16.
I can put it there, or I can put it here, because I will do. I'll put the. Yeah, that's like is. Let's say. Okay, I wanted to show you another way of interpolating data. So interpolating, you could think of it as learning from your data points, right? When we did the polynomial, we learned from our data points about the regions in between. We were learning what the values of a smooth function would be in between. When we did the cubic spline, we were learning from the data points what the value might be in between the data points. So machine learning is a form of interpolating, learning from a set of data points. So I just wanted to show you an example, because I haven't touched on machine learning at all in this class, but I just wanted to end up with an example because it's becoming so important. Machine learning for interpolating, because one way of thinking about machine learning is it really is, or at least in many cases, a interpolation process, but not with cubics or piecewise cubics, not with polynomials, high order polynomials, but with a network of neurons where each neuron is really a function that we call an activation function. And there are various mathematical forms for the activation function. So it's kind of a piecewise, think of a neural network as a piecewise collection of functions, activation functions, representing the neurons in your neural network. Okay. So here's a example of a neural network that we might apply to our three data points or a homework assignment with, I think there's 8 or 10 data points. We got a set of independent measurements in their corresponding dependent values, so xi's and yi's, and we want to interpolate between the xi's and the yi's. In a neural network, you might arrange a network of neurons to do that interpolation. So in this slide here, the left and the right are my data points, my xi's and yi's, and in between here, I've got 4 neurons. And these 4 neurons are connected to the input and they're connected to the output. So these black lines represent connections.
Are they the full sets or just for each data point?
This is the set of data points. So this represents like the
three.
There's 3 data points.
Okay.
Yeah. And the homework be 8 data points. And the yi are the 3 data points for the dependent variable, or 8 data points for the dependent variable. And so we're going to try and interpolate the pattern of the data with this neural network. So the one way of thinking about the neural network that's sort of analogous to how we thought about the spline or how we thought about the polynomial is that each neuron here is a function. It's actually a non-linear function. Typical functions I pictured down here. So it's this, each neuron has a function like this that translates its input into its output. Each of these connections, we give a weight. So we can weight more strongly or less strongly a input connection to the neurons here, this layer of neurons, which is called the hidden layer. And then there's a bunch of weights over here on these connections. So every connection has a weight, and then every function has an additional, every neuron has an additional function that's called a bias that kind of lifts up and down these activation functions here. But you could think of this as trying to find a superposition of, say, this function here, where each of these 4 neurons to interpolate the data. There's those three data points to match the dependent variables. So let me just go to the code. So I think I'm just advertising this as something you might be interested, and maybe you already know all this, but you might be interested in exploring it. And advertising is a way of thinking about machine learning. So this is still my cubic spline example code, but I added a additional example where I'm going to interpolate between the three data points with a neural network. And that's the blue line here. The dashed yellow line is that piecewise spline. So Python has a whole, fully developed package for Torch for machine learning. So I'm just importing some functions from that. I have to use Torch, I'm going to slightly modify the form of the input data. I had the input data in, I think, NumPy arrays. You need to put it into a Torch tensors. But that's all this line does here. And so I wouldn't worry too much about this first line here, but it's taking the array X and the array Y, my data, and putting it into X train and Y train, which are torch structures, torch tensors that it will use in this process. So that's just a manipulating of the data, putting the data in a different form. This little bit of code here defines the neural network that I'm going to try and interpolate with. So I'm trying to interpolate with a network that looks like that network I showed you in my slide. I'm going to I've got one independent variable input, xi, and I've got one dependent variable output, yi. And between these data points, I'm going to have one hidden layer of neurons. And my only variable here is how many neurons in the hidden layer. And right now I'm using 3 neurons in the hidden layer. I think in my sketch of the hidden layer, I had 4 neurons there. So to define that arrangement is done with this little bit of code here. So the value of H is just my number of hidden neurons. So I'm going to use 3 hidden neurons. This line here, so this is a call to one function that sets up the neural network, sets up the structure of the neural network. It's going to have one input that feeds to, in my case, H is 3 neurons, hidden neurons. Then those 3 neurons in the second call, those feed to my one output. So this kind of defines this structure: one input, 3 hidden neurons, one output. Those hidden neurons have this associated with them, this activation function. There's various activation functions that are used in machine learning. They have the property that they're non-linear. That's an important thing about the activation functions in neural networks. So they're not linear, they're non-linear. I'm picking one of them that I showed you on the plot, KMH. So this has set up the neural network. I'm going to train the parameters of the neural network. So remember, each connection had a weight. There were 3 input connections to my hidden layer. There were 3 output connections to my hidden layer. So that's 6 weights. Each of the hidden layers neurons has a function associated with it, which comes with a bias. So there's 3 more parameters. The output neuron also has a bias. So there's 10 parameters in total. So there's 10 parameters in here. We're going to use our data to adjust the values of the parameters, the 10 parameters to match our data. So this is, it's just like least squares fitting. In least squares fitting, we match some parameters to some data points. And here we're matching the parameters associated with the neurons and their connections to the data points. So these 2 lines of code here, this says we're going to do least squares for optimization of the parameters of the neurons and the connections to the data. And this call here just says, how are you going to do your gradient descent to find the minimum chi-squared? Here we call it a loss function. So find the minimum loss function to decide that you've matched your parameters to your data set. You trained your parameters on your data set. This is gradient descent, which we talked about in fitting. This is stochastic gradient descent, which we talked about as one way of walking your way to the minimum of chi-squared, which is just kind of taking random steps around. And if you find you're going downhill, go that way. So this just sets up the kind of things that we did in least squares fitting, where you've got you're going to fit based on a chi-square, minimizing the chi-square. So you define what you're going to minimize, and then you've got to have a procedure for walking towards the minimum, and that's this guy here. So we got the network, we got how we're going to find the optimal values of the parameters, and then this loop here just goes round and round this loop. For the given set of parameters, for the parameters being, the biases and weights, it's going to calculate the predicted y values from the x values. So it's going to make your prediction. It's going to calculate chi-squared. This is the second line here, although we're calling it a loss function here, but it's just like a chi-squared function. We're going to calculate the slope of the chi-squared at current location, and we're going to take a step in the chi-squared down the chi-squared hill at our current location, and that's basically what these lines here do. I won't go into the details, but this is taking a step in chi-squared, so we're updating our parameters. We're changing our parameters, and then we just go around and around and around in this loop to find the best values of the parameters. And so when I did that, this here is just a detail. Remember at the very beginning, I had to convert in my X and Y arrays into the language of torch. The output of torch, I converted it back into the language of X and Y arrays. That's all this is. But anyway, when I run this result, this blue dashed line, remember we had 10 neurons. We adjusted the parameters on our 10 neurons to go smoothly through this data set here. So this is a neural network interpolation of the data, just so you get an idea for that. And it's pretty easy to construct, especially if you know a bit about fitting and how you build fitting procedures up to construct a neural network and do interpolation with neural networks. So this is just to give you an example of that.